Students and faculty members, it is my privilege to introduce Sir Michael Atiyah of the University of Edinburgh. Sir Michael Atiyah is one of the most influential mathematicians of our time, and he really needs no introduction. However, I would like to take this opportunity to tell our postgraduate students that if you get stuck with your thesis work, try to read Atiyah's collected works for inspiration and encouragement. That was what I did when I was a postgraduate student, and it really helped me then. So Michael Atiyah is an old friend of our university, and he has given many wonderful lectures here in the past. Today's talk is titled Geometric Models of Matter. In view of Britain's long-standing tradition of mathematical physics that goes back to Isaac Newton in the 17th century, and particularly flourished by James Maxwell in the 19th century, one might not be surprised why Sir Michael Atiyah is interested in physics now. On behalf of Professor Moy and the Mathematics Department, let us welcome Sir Michael Atiyah.
Yeah, you can. Where was the? Oh, it's coming down. Right, so this is my talk, the title of my talk, and as you see, it's joint work with two colleagues who are both physicists. So it's joint work between mathematicians and physicists. It is the topic. We've written a paper which will appear in the Proceedings of the Royal Society, I hope quite soon. But let me give start with some historical background to set the scene for what it is we're trying to do in this paper. I should say this paper is a very preliminary exploration of an idea, not a final theory. It's very speculative, so don't put this in any exam papers. You'll get failed results. So now let's start with some little bit of history. As we know, one of the great achievements of Einstein was to explain gravity as the curvature of space-time. It's a beautiful theory mathematically, geometrically, and it has been remarkably successful in predicting correct physical results for 50 years. It's one of the theories which was, when it was produced, there was very little need or evidence for a new theory of gravity, but Einstein felt it was necessary for fundamental reasons, and 50 years later there are hundreds of experiments which justify the theory very, very accurately, including every time you use your satellite navigation for your car or things, you use the general theory of relativity. Now this theory is a theory about the curvature of space and gravity. And in the equations of state for the Einstein theory, there's a left-hand side, which is the curvature, and the right-hand side in the vacuum is zero. But when you have matter, then the right-hand side contributes a term called the energy momentum tensor. And Einstein always said the left-hand side was beautiful, but the right-hand side was junk. And he didn't like it. Well, and ever since Einstein's time, people are trying to understand the nature of matter. What is matter? How does it link with gravity? And what theories can you develop? And there's a lot of work being done, and some people think the theory is nearly finished. Some people think it's a long way to go. And I'll talk a bit more about it as we go on. Now, after Einstein's theory of gravity, there was an interesting step developed by Hermann Weyl, a famous mathematician, and followed up later by Kaluza Klein, some physicists. What Weyl did essentially was to propose that you could understand electromagnetism. The theory was given by Maxwell's equations. He could understand that in a similar way to gravity as a curvature of an extra dimension. So you have 4 dimensions of space-time, and if you imagine a 5th dimension, then the curvature from that direction could be interpreted as the electromagnetic field. It was a beautiful idea, and Weyl submitted the paper to a journal, and they sent it to a referee, who was Einstein, and Einstein said, it's a beautiful idea, but it's wrong, because it conflicts with fundamental facts of physics. In Weyl's theory, as you moved around in a magnetic field, lengths could change. And so Einstein said, if that was the case, then different hydrogen atoms now would have different properties, different mass, depending on their past history. And we don't see that. So the theory is physically incorrect. But Weil thought his theory was so beautiful, he insisted, and the editor was very tolerant. Nowadays, editors wouldn't do that. And so they allowed him to publish his paper, and they put Einstein's rebuttal as an appendix. So there's the paper, and Einstein at the bottom says, this is all rubbish. But fortunately for Weil, a few years later, quantum mechanics appeared, with Niels Bohr, one of the prime figures. And in quantum mechanics, it led you to make a different physical interpretation of Weil's equations, so that it wasn't the length or magnitude that changed, but it was the phase of the wave function. And this is something which you cannot detect. And so there's no contradiction with physics, and so the theory was okay. And so Einstein's objection disappeared, and in fact, gauge theory became fundamental to all subsequent theories of physics. So the incorrect theory, which could have been thrown out by the referee, fortunately was saved, and it was the foundation stone of subsequent theory. Interesting lesson to learn. Don't always trust the referee. And I mentioned here Heisenberg as another great figure in the development of quantum mechanics. Now, quantum mechanics saved Weil's theory from, enabled you to combine it with Einstein's theory of gravitation very successfully, but on the other hand, it introduced totally non-geometrical ideas. Quantum mechanics was not about geometry, it was about operators and Hilbert space, a lot of complicated machinery, and Einstein didn't like it. He didn't like quantum mechanics, he didn't like the foundations of quantum mechanics, and he had long arguments, particularly with Bohr, which went on for their whole lifetime, in which they would argue about quantum mechanics and was it correct and so on. And even to his last days, Einstein never accepted quantum mechanics as a fundamental theory. He says it gives you good results when you use it, but it's not fundamentally philosophically sound. And there are some people who still believe that today, including myself. So I'm an Einsteinian. Now, the current theories of matter, orthodox theories, are built up out of gauge theories, which is the theory initiated by Hermann Weil, but instead of using the circle group, the unitary group U1, you replace it by non-abelian groups, matrix groups, SU2, SU3, different ones, and these equations that you get now are called the Yang-Mills equations. They are the counterpart of Maxwell's equations when you replace U1 by these higher groups, and because these larger matrix groups are non-commutative, the theory has become non-linear. Maxwell's equations are linear, the Yang-Mills equations are non-linear, and that's essential for various properties of matter. So this is the framework in which modern physics takes place, and some people think it's nearly finished, and we just have to wait a few more years, and one or two more experiments at CERN, and we'll pack up and go home. And there will be no physics jobs anymore for anybody. But I'm more of an optimist. I think there will be jobs still for physicists to do. And I think there's some hope there that although the modern theories explain an awful lot about physics, there are still some awkward embarrassments. There are things called dark energy and dark matter, which are an embarrassment to physicists because they say that we only understand 5% of the mass of the universe, and all the rest of it we don't see, we don't know about it, and yet they believe their theory is correct. So there's somehow a contradiction between the enormous gaps and yet their confidence in the theory. So they think that one day they can fill these gaps very quickly. Other people think you need new ideas. So it's open for debate. Now, long before the present theories of gauge theories were developed, going back in the 1930s, the British physicist Tony Skyrm put forward a nonlinear model, classical model, of the proton and neutron. And this was a very brilliant idea, which had profound implications subsequently, and it was the first example in physics of this kind of physics of what are called solitons. These are solutions of some nonlinear partial differential equations which are highly localized and behave as though they were particles in some sense. And so here, Skyrm's model is a model for the proton, say, but doesn't distinguish between the proton and the neutron, and it's defined by a field F defined on three-dimensional space, which takes its values in the group SU2. So in the 2x2 matrices, unitary matrices of determinant 1, which is a three-dimensional sphere. And as you go to infinity, you assume that this field goes to a standard position, which means that it goes to the value 1, the unit element in the group. That's the model, and then it's subjected to some energy function, which gives you minimize the energy to get equilibrium states and so on, and then you can put in time and write down dynamics. So the fundamental object is a field which is nonlinear because it takes its values in the three-dimensional sphere, not a linear function. The interesting thing is, from fundamental point of view, is that if you map the three-dimensional sphere, three-dimensional space to the three-dimensional sphere, and you make it go to 1 at infinity, it's geometrically or topologically the same as mapping a three-dimensional sphere to a three-dimensional sphere, because you compactify three-dimensional space by adding a point at infinity, just like you can compactify a straight line into a circle by joining the two ends together. And if you do that, then if your map is continuous, then such a map has a degree, the number of times the three-sphere initial space winds around the three-sphere in the target space. Like if you map a circle to a circle, the winding number is an integer, which can be positive, negative, or 0. So here there's a topological invariant, which can be positive, negative, or 0, an integer. And this, in the Kerr model, describes the number of protons, the barrier number. So the fundamental, if you're studying matter, the fundamental content is the number of protons you've got, and this is, in this model, has a topological significance. Not the first time topology comes into basic physics. The first time topology enters into physics was by a famous argument of Dirac, which explained that the quantization of electric charge was fundamentally a topological phenomenon, which is related to the winding number of a circle to itself. This is the analogous thing. It describes not charge, but baryon number, and it's related not to the winding number in dimension 1, but the winding number in dimension 3. So anyway, the theme of my talk is going to be really to focus on these topological starting points of models of physics, because long before you do anything more complicated, like study the energy and dynamics, you start with a number of objects, number of particles, and these are conserved in the system, and they behave like particles that, in some naive sense, bounce around and don't disintegrate. So this is the topology is going to be the basis of my talk. I'm not a topologist, but I became a topologist, so to speak. So this is the degree of the map is described as the baryon number. This is the basic fact of the Kerr model. And then you write down a certain energy function, which I won't write down, and then it leads to the dynamics of interacting particles. So now I want to give some new ideas, which is very speculative and only preliminary, and it's an exploration. I won't think this is a theory. We're trying to explore some possibilities with some vague aim. And if we get very far, we will develop it further, but it will be a new point of view on physics, a little bit like the Kerr model is not regarded as fundamental in physics, is regarded as some approximation to a description by classical methods of what baryons are, but it can be very useful. For example, the Kerr model has been very extensively studied as a model for real shapes of nuclei. If you do nuclear physics, then the general theory doesn't tell you very much about what actual nuclei look like. If you're a hard-nosed experimental physicist, you look at nucleus, you try to get something about its shape, its properties. The general theory is not sufficiently good. And so you use these more elementary models like the Kerr model. You can use them to guide you to find real pictures or real ideas about the structure of iron or hydrogen or other particular nuclei. And so the speculative idea is I want to go beyond that, go beyond the Kerr model, but something slightly more complicated. But in the first instance, I will ignore time. So I'll be describing just the model that gives you static objects. Secondly, I'm going to now adopt the Kaluza-Klein idea, or the Weyl idea, as generalized by Kaluza-Klein, to bring in a fifth dimension, which now enables us to incorporate electricity and magnetism. So now we'll not only talk about baryon number, we also talk about charge. And we'll combine the bits of topology I mentioned before, the topology due to Dirac that interprets charge in two-dimensional terms, and the topology due to Skirm, which helps you count baryon number in sort of four-dimensional terms. Now this fourth dimension, fifth dimension, 4 dimensions other than time, is thought of as being a circle. So you take your three-dimensional space and you multiply it by a circle in another dimension. But this description is only meant to take place asymptotically very far away. In some intermediate region near where your proton is located, something more complicated takes place, as happens with solitons. So asymptotically, you separate out the extra variable, but in the middle, all the variables are mixed up. That gives you a lot more scope. Now, the next thing I'm going to do in this model, which is, well, a reason I don't fully understand myself, but basically, the roles of electricity and magnetism are going to be interchanged. Now, electricity and magnetism are fundamentally dual in Maxwell's equations, and there are lots of parallels, and so the duality between electricity and magnetism is well known in physics in general. So we're going to interchange the roles of electricity and magnetism. Now, all this will lead us in the direction of, if we ignore time, we're only left with 4 dimensions, the 3 dimensions of real space, and the 4th dimension, which is this circular dimension. So we'll reach the 4-dimensional space. Now, this 4-dimensional space is different from 4-dimensional Lorentz space, because we have all our directions are space-like, including the circle. So the metric on it is positive definite. It's a Riemannian metric, not a Lorentzian metric. It has fundamentally different properties. So we led into the direction of 4-dimensional Riemannian geometry, not 4-dimensional Lorentzian geometry. If you like, it's part of a 5-dimensional Lorentzian geometry, but we've thrown away time, so we're talking about the spatial part of it. Now, one of the reasons I like this starting point is that mathematicians have learnt from Donaldson, my student, who took ideas from physics, from Yang-Mills theory, and showed using that 4-dimensional geometry is quite remarkable. It has unique properties not present in any other dimension, and in fact are independent of the choice of the Riemannian metric and depend only on the underlying shape of the space. And there are beautiful results in 4 dimensions which are very deep, not fully understood, have some mysterious connection with physics, and are really there to be exploited. And so my vague hope, one of the hopes, I have a lot of vague hopes, and I hope at least one of them will work, is that these deep results of Donaldson will somehow reflect themselves in properties of the physics of which this is meant to be a model. So these are going to be models of matter. Then these beautiful results of Donaldson should have some rather good contact with the physics of those models. Now, this theory of Donaldson, which was developed from the Yang-Mills equation, was subsequently shown by physicists, Seiberg and Witten, to be equivalent to another theory, which is called the Seiberg-Witten theory, which leads to the same results, and in some ways is much simpler. And this theory looks a bit, well, even better from the point of view of physics, because the Donaldson theory involves looking over a space of 4 dimensions at Yang-Mills fields, let's say with group SU2. But the Seiberg-Witten theory involves looking not at a non-abelian group SU2, but just ordinary electromagnetism, U1, but you couple it with spinors involving the Dirac equation. So you get a theory which is very naturally a coupled theory, spinors and electromagnetism, coupled in a nonlinear way, and the solutions of that give you information about the geometry which is the same depth as the Donaldson theory, but looks much more directly tractable if you want to relate it to physics. You don't need to bring in non-abelian gauge groups. You can just work with classical electromagnetism and spinors. So the first objective of this investigation is to say, well, if you go to this other picture, we want to get more than the Skirm model. We want to get precise models for let's start with the basic particles. So we want models for a single proton and a single neutron. And we want them to be different. In the Skirm model, there's no difference. The soliton with degree 1 is the proton or the neutron. You can't tell. There's no electric charge built in. But now we've built in charge, and so we can ask for a different model for the proton and the neutron. Secondly, we're not going to have a model only for baryons as a Scum model. Our model also should include leptons. In other words, things like the electron and the neutrinos. So this is a more ambitious model. If you can make it successful, it goes further in identifying the fundamental properties of particles, both the baryons and the leptons. And so it improves on the Scum model by incorporating electric charge, and it also incorporates leptons. And now let me just give you a quick summary of the parts of Riemannian geometry that we want to use. I mean, we've got to a four-dimensional situation where we have Riemannian geometry at our disposal. So now we want to know what are the basic ingredients in four-dimensional Riemannian geometry. Now, Riemannian geometry has some properties in all dimensions. It's always true that the Riemann tensor, which describes the curvature of the, you have a manifold with a metric that defines curvature. The curvature is a complicated tensor, but it has two parts to it. One part is called the Weil tensor, and the other part is called the Ricci tensor. Now, these two are very different. The Weil tensor is the part that is conformally invariant. In other words, if you take two metrics and you change the scale, by a scale it depends on position, not just a constant scale, change the metric by a function, then the metric changes, but the Weil tensor part does not change. The Ricci tensor part does change. So the Weil part is the part unchanged. It presents only on the conformal structure. For example, in a Riemann surface case, the conformal structure is just the complex structure, not the metric structure. The Ricci tensor, on the other hand, is the part which enters into Einstein's equations. You put Einstein's equations and say the Ricci tensor is either 0 or it's a constant, and then it's a scalar number, which could be positive or negative or 0. So those are the basic ingredients, and that would be true in any dimension. So the Weil tensor is conformally invariant. Now the Weil tensor happens in dimension 4, and only in dimension 4, for obvious reasons, to break up into two parts. It's what's called the self-dual and anti-self-dual parts. They depend on a choice of orientation in the four-dimensional space, and when you change the orientation, you flip these two round. It's closely related to the simpler duality between electricity and magnetism in Maxwell's equations. And the Weil tensor can be thought of as a exterior differential two form with values in something else, and this is the duality of two forms in four dimensions. It just takes a two form which corresponds really to two directions to the orthogonal two form. So it depends on the fact that 2 is half the dimension, only happens in dimension 4. So this is a peculiar property in dimension 4. Now, because of this peculiar property in dimension 4, you can look at a particular class of manifolds, which is a particular class of metrics or conformal structures, which require only one of these parts of the Weil tensor is not 0. The other part is pretty equal to 0. This is a strong restriction, of course. It cuts down, but nevertheless, there are lots of manifolds with this property. It's by no means an empty class. And now, so our first sort of experiment in exploratory theory is to choose as models of matter manifolds of this type. Manifolds which have a conformal structure or a metric in which half the Weil tensor vanishes. That depends on the orientation. If you change the orientation, you go to the opposite equation, which then you would interpret as antimatter. So changing the orientation will correspond of the four-dimensional space, which, don't forget, involves both spatial orientation and the circle variable. That corresponds to going from model of matter to model of antimatter. Now, the other thing which happens in four dimensions is a very beautiful theory developed by Roger Penrose, which is a very beautiful theory mathematically, has physical intuition as background, which Penrose, physicist, and it's been promising in a number of ways, but there may be other things you can do with it. So the Penrose twistor theory does the following. If you have a four-dimensional manifold which is self-dual, in the sense I've described, half the Weil tensor vanishes, then this enables you to construct a twistor space. The twistor space Z is a space of 6 real dimensions, 4 for M, and 2 more for a two-dimensional sphere. So this Z is 6 real dimensions, but also turned out to be complex 3 dimensions. You introduce in a natural way complex 3-dimensional coordinates, and is a complex analytic three-dimensional object. M itself is not complex, but when you add in the extra two-dimensional variables, it becomes complex. And moreover, Z is fibered over M with a two-dimensional sphere as fiber. So locally, it looks like a product of the manifold M with a extra two-dimensional sphere. It's a bit like adding the circle in the Weyl theory, but you add a sphere here. The sphere itself is, of course, naturally complex. It's the Riemann sphere. And these appear as complex sort of the lines in this three-dimensional space, but the space that parameterizes these lines is real, it's not complex. And then the third piece of information is that you have on this complex manifold a antilinear map, a map which takes complex into anti-complex, holomorphic to anti-holomorphic, and square is 1, just like going to the complex conjugate of a variable. And on each sphere, it corresponds to an antipodal map on the sphere, just like the antipodal map on the complex sphere is antilinear. And the beauty of Penrose theory, and this is summarizing a beautiful theory, is that the information of this complex manifold of dimension 3 complex variables, with the additional bit of information about this antilinear structure, it encodes entirely the conformal metric structure of the manifold M and the Einstein equations. It can be all described in terms of complex theory. So the beauty of the Penrose theory is that it enables you to replace real manifolds and real differential equations by a theory of complex variables in which there are no differential equations. The differential equations have been eliminated and replaced by requirements of being holomorphic. So it's pure geometry in the sense of algebraic geometry of the complex numbers and things like that. So it's a very beautiful theory. It applies only when half the Weyl tensor vanishes for these cells. But those are the models we want to take. Now, the basic example, I always tell my students, whenever you have anything, you must always first the first elementary example, and the first example should be interesting. There's no use saying I have a general theory, and the most interesting example is the empty set or zero. You must have a good example of instance. And the basic example of the Penrose twistor theory is given by the manifold being the four-dimensional sphere with a natural round metric. Then it turns out that this space Z is the complex particular three-dimensional space. Just 4 homogeneous coordinates, complex variables. And then you can describe very easily exactly how they're related. But in this case, well, I'll give it to you. How you think of two-dimensional complex space, which is the same as four-dimensional real space, as one-dimensional quaternion space. H stands for the quaternions, introduced by Hamilton. And just like there is a complex projective line, which is a two-sphere, there is a quaternion projective line, which is a four-sphere. So the HP1 stands for the fourth sphere, and if you take the complex projective 3 space is the space of complex lines in C2 through the origin. And if with every complex line you associate its quaternionification, add 2 more variables, you get a point in the quaternion projective line. That's the map from CP3 into S4. That is the basic construction of the Penrose theory. In this case, because the four-dimensional sphere is actually conformally flat by stereographic projection, both W plus and W minus are 0. So in fact, there are 2 twistor spaces you can make, one spheric left-handed, one right-handed. They both exist. That's rare. In fact, it only happens in examples like this. But you can see that it's really quite elementary. You write down a formula, you write down equations, and this then leads to a lot of very nice mathematics. So the first example is already non-trivial. And the whole problem, what it does is convert Riemannian geometry into holomorphic geometry. Now here you have a good analogy with Riemann surface theory. Riemann surfaces are two-dimensional objects. If you give them a metric, a Riemannian metric, they have curved surfaces. Underlying the metric, there is the conformal structure. And the conformal structure in dimension 2 is the same as a complex structure. It measures angles rather than distances. So in dimension 2, Riemann surface theory is the theory of complex geometry associated to real geometry. But when you go from dimension 4, you see you need to have more dimensions to work like that. And the philosophy is the following. In 4 dimensions, of course, you can, if you have two dimensions, x and y, or you write x plus iy, it's a complex variable. And it doesn't matter which x and y you start with, you really get the same complex variable. If you have 4 dimensions, x1, x2, x3, x4, you can make 2 complex variables out of them by saying x1 plus ix2 or x3 plus ix4, but you can permute them another way. You get another set, or more than that, you can rotate. So you get a lot of choices of how to put complex coordinates into 4-dimensional space, and they're all equally good. So what you do is you use them all, and the parameter that distinguishes them is the x of 2 sphere. So if you think as you move up the 2 sphere in the horizontal direction, you put in the complex structure determined by that point, and then the beauty of it is that those 2 complex variables together with the complex variable of the sphere itself make 3 complex variables, and now they're all on an equal footing. You have a hidden symmetry, as the physicists sometimes say. So that the analogy with Riemann surfaces is very strong, but the twistor theory is much subtler. In both cases, however, you have the situation that the complex structure you put on, for example, in the Riemann surface case, a complex structure you can put on a surface has parameters which distinguish one from the other. They're called moduli. For example, if you take the first interesting example of Riemann surface torus, in the case of genus 1, it has one complex parameter called the complex modulus, which enters the theory of elliptic functions. And if you increase the genus, the number of parameters goes up. Similarly here, there are complex parameters that describe the possible variations of from a given family. And there is, again, there's only finitely many parameters. And whereas in the Riemann surface case, the important bit of topology is played by the one-dimensional cycles that go round a torus, so that's one horizontally and vertically, say, and for a higher genus, you have many larger homology group. In dimension 4, as you might expect, the role of the first homology is played by the second homology, thing in the middle dimension. And there's a very analogous theory machinery there. Now, Riemann surfaces have the beauty that if you should have pictures of a Riemann surface. If you imagine here is a big surface, let's take a surface with 2 holes in it, so it has genus 2. Then you can take scissors and cut it in half, and pull them apart. And what you've got in each case is a surface of genus 1 with a hole cut out. So you can get a surface of genus 2 by taking 2 copies of a torus, cutting little holes and gluing them together, and you get a surface of genus 2. And this can be carried out precisely. And this is called a connected sum, and you can repeat it. So in fact, every surface of higher genus can be obtained by taking a certain number of copies of the torus and just gluing them together. The corresponding thing works for this twistor story in higher dimensions. You can make connected sums, but it's not always possible. There are sometimes obstructions, and there is a very precise theory telling you when it's possible, when it isn't possible, which has been well developed by people in complex analysis. So there's a very good theory of how you can make connected sums, or the other way around. Think of it as this way: you have some object-dependent complex structure, and you can vary the moduli. You can shift the parameters, and in the limit, when one parameter goes to 0 or infinity, they split apart. So you can break things up. That's the opposite of gluing them together. So this the idea would correspond to the way in which matter, if these are models of matter, could decompose into smaller pieces. So the decomposition of large things with large nuclei into small nuclei could be modeled, hopefully, by the way these manifolds break apart. And we know very precisely how that happens, so there is a mathematical machinery that is actually available. So the long-term aim of this program, long-term, long after I've left this world, young people here will follow it up. So if it works, it would be to use these twistor spaces to model the interactions of matter. And the geometry in which these things break apart would describe the possible decompositions of matter. This is still giving what you might call the kinematic theory. It's not studying the forces that do it, just telling you the possibilities of how it could happen. The underlying topology and the complex analysis will give you various possibilities, and hopefully the forces you introduce would actually correspond to the stretching process by which the surface can decompose and break apart. That would be the long-term aim of having a classical picture of nuclei that can fuse together and break apart. And in the course of that, we're tracking both the baryon number and things like electric charge. Now, the first big warning here is that this theory is very much distinguishes between matter and antimatter, because if you've chosen the right orientations, all the matter occurs in one class. There you have twistor spaces. You can glue them together. If you choose the other orientation, you get the antimatter, and you can't do this gluing together holomorphic geometry between the holomorphic variables and the anti-holomorphic variables. They're separate. So it's a much more difficult story. So the interaction of matter with antimatter would not be easily done by this method. It'd be a big challenge to do it. It would, on the other hand, it would do very well to explain, or hopefully, the interactions of matter with itself, or correspondingly, of antimatter with itself. That's, well, a very reasonable objective. Now, I haven't said anything about compactness. In Riemann surfaces I talked about were closed things, like sphere, torus, and so on. And now you can ask with these four-dimensional manifolds, what kind of conditions do we have? Are the manifolds going to be compact, like the Riemann surfaces? And the answer becomes a bit more interesting. So first of all, we're going to distinguish between models which have charge and models which are electrically neutral. So a model for an electrically neutral particle, like the neutron or the neutrino, those can be compact. They'll have no infinity. They just close up. They don't go anywhere. But models of electrically charged particles, like the proton and the electron, they will be non-compact. They'll go off to infinity. But they will be complete. Let's say the metric, it takes you infinite length of time to get to the end. You never get there, like a long cylinder. So, rather different, and that's very fundamental for the geometrical interpretation of charge. Has to be like that, as I'll see in a moment. But nevertheless, they're the kind of manifolds which are described here. If they're compact, they're easy. If they're non-compact but complete, they're still ones you can study carefully. Then next question you can ask about is symmetries. Symmetries play a very important role in all physics. They sort of more or less dictate the progress of physics by different interpretations of symmetry in all sorts of ways. You have the symmetries coming from space, rotations and translations. You have symmetries of the Lorentz group. You have internal symmetries of particles. So symmetries are fundamental, and so you have to say what kind of symmetries you expect of your basic particles. And if the particles are modelled by manifolds, you have to say what kind of symmetries the manifold should have. So the first basic idea here is that all the four basic particles, I've just lumped them, I haven't talked into complications of higher generations and so on, but the four basic particles, electron, proton, neutron, neutrino, all of them should have rotational symmetry, SO3 symmetry. You know, the most basic symmetry you've got, and they should all have that symmetry. Now that, of course, will restrict the kind of manifold you can get, because the symmetry will have to preserve the geometry, it'll have to preserve the Riemannian metric. So if you have a four-dimensional space with a three-dimensional symmetry group, then that cuts down the degrees of freedom a great deal. And if you want to solve differential equations, you'll be led to ordinary differential equations instead of partial differential equations. In particular, we want to have manifolds of Selfdual and Einstein. I put it now this condition, Einstein manifold, into the manifolds. And this gives you a very restricted class of possibilities. We want to find fundamental basic particles that are more or less unique. And then I want, well, the Einstein equation says that it could be a scalar curvature, and the curvature could be zero or could be not zero. And here the same statement is that there will be zero scalar curvature in the non-compact case. But in the compact case, that would be too strong. For example, the sphere has a positive curvature. The plane has zero curvature. So non-compact things can have zero curvature. Compact ones can't, really. And the curvature should be positive in the compact case, like the sphere. So now let me give you some compact models, easy ones to start with. And so we'll give, first of all, a model for the projective plane and for the neutron and for the neutrino. Now, this is a very first approximation. I don't take it too seriously. But going along this line, these are the easiest choices. Then you can begin to ask questions. Are these too simple? Should you complicate them, do something else? But let's start with this as a start. So the neutron, which is in a way the most basic particle, it has baryon number 1 and no charge. That will be, in this model, described by the complex projective plane. Complex projective plane has a standard metric invariant under the symmetry group. It has a large symmetry group. The symmetry group is in fact SU3, and it's very well known space. That would be the model for the neutron. And the important point to bear in mind is the neutron, the predictive plane on the hand, is actually not topologically trivial. It contains within itself predictive lines, and those lines are determine the second cohomology or homology of the space. So they're topologically interesting, and that's what makes this baryon number non-zero. The neutrino, on the other hand, in this model, would just be a four-dimensional sphere. It would have no interesting topology, no second homology, and that corresponds to baryon number 0. It's not a baryon. Neutrino is a rather difficult object to find, as you no doubt know. It has no charge and no baryon number. These two manifolds obviously have very large symmetry. Certainly it includes SO3, but it's actually bigger. The symmetry of the first one is SU3, symmetry of the second one is SO5. So they're very good. And they have the right kind of metrics which satisfy the conditions we required, that I mentioned, Selfdual and Einstein and so on. Now, I put in a little stop press here. Well, actually, stop press is a bit old now, but it's never mind. It's still true. One thing you might want to do, and I thought about this, is to replace this complex vector plane by a slightly different version of it. It's a rather interesting version. It's a manifold which was discovered by Nigel Hitchin. Very explicit formulas for this metric, depending on an integer parameter n. And when you have, if n is equal to 2, you get back the metric of the complex vector plane. But if n is bigger than 2, what happens is that inside the complex vector plane, there is the real predictive plane, just by taking coordinates to be real. And that's a surface inside the 4 dimensions. Alongside that surface, the thing acquires a kind of edge. If you take transversal section to that, you get a 2-dimensional picture which looks like a cone. So it's a cone moving along the surface, giving you 4 dimensions. But in the transverse direction, it's a cone, and the angle of the cone depends on n. The angle of the cone is 4 pi over n plus 2. So n gets bigger and bigger, the cone angle gets smaller and smaller. If n is 2, you get pi, which means there wasn't a cone at all. It's a nice smooth metric. The space remains always the same, the complex vector plane, but the metric is acquiring a bend, an angle. If you go to the limit of n equals infinity, then the manifold becomes non-compact, but the metric survives, and we'll see that in a moment. So now let's go to the non-compact models. Now, first of all, we have the electron. Now, actually, this electron model is one which is well known to physicists, but usually it's interpreted in terms of the magnetic fields, and it's thought of as the model of what's called the Dirac monopole. It's given by a manifold which is well known to geometers and physicists called the Taub-Nut manifold. It's a very odd name. It's half an acronym. NUT stands for 3 different mathematicians whose names begin with N, U, and T, and Taub is another mathematician. His name is given in full. So it's not really an acronym, but it's half an acronym. Anyway, this is a very well-known manifold. It depends on a parameter, which is sometimes called its mass, which is 0, and it is, if you replace electric by magnetic, it's the picture of what people call the Dirac monopole. And what it amounts to is that topologically, it's just flat space, C2. But when you go to infinity, you change the metric, so instead of becoming a 3-dimensional sphere, getting bigger and bigger, you fix one of the circles in that 3-dimensional sphere, keep it of constant size, and what you get is a circle bundle over the 2-sphere, famous Hopf circle bundle. As you go to infinity, it looks like a circle over a 2-dimensional sphere. And that's what the things are supposed to look like asymptotically at infinity. The circle will have fixed lengths. The length of the circle will correspond to the parameter m. If you make those circles go to infinity, you get back to flat space. If m is some other number, it's different space, different metric. So there's no topology in this space. The space is topologically uninteresting. The only thing that's interesting is that you change the metric. So at infinity, it's not uniform in all directions, but in one direction it has constant length, the other direction it blows up. And that explains why this has a charge, no baryon number. The baryon number would correspond to having some interesting topology. It doesn't have interesting topology. Baryon number is 0. But the charge corresponds to the fact that when you go to infinity, you get this interesting bundle over the 2-sphere with the circle bundle, which is non-trivial. It's not a product. It's because the total space is a 3-sphere, not S1 times S2. And that is the explanation of the charge. So the charge is built into the topology to infinity. I'll say a bit more about that in a moment. So asymptotically, this is the picture, the vibration 3-sphere to the 2-sphere with fiber S1 is what this link looks like. Now, the other model we want is the non-compact model of the proton. So the proton should also be given by a nice manifold with a nice metric. It should be not compact. It should be Einstein and so on. It should have SO3 symmetry. And by good fortune, there is one manifold. And that was discovered by myself and Nigel Hitchin some years ago when we were studying the problem we didn't even bother about, but it was trying to work out the moduli space of SU2 monopoles. And we found this manifold, and it had these remarkable properties. What it turns out to be, it is actually what you get from the complex projective plane by removing the real projective plane and putting on it a certain metric. In the complex projective plane metric, the real projective plane would be at finite distance. But you stretch it out. You stretch it out so it becomes a long infinite cylinder, and this metric does that trick for you. And what it is, in fact, it's fibered over. But the metric at infinity is the same as you get from the metrics of Hitchin I mentioned when this parameter n goes to infinity. I told you start with a complex projective plane, you take the real projective plane, you put in cones over it, and they make the angle of the cone smaller and smaller. Eventually, when the angle goes to 0, it shoots off to infinity, and you get the metric I've been talking about. So it's a very nice metric, and these are unique. If you want a metric that is Einstein, SO3 invariant, etc., that's all there is. So, we don't have to force it to be like this. It has to be like this. So, now here, the proton, you see, looks very similar in one way to the electron. It has a behavior at infinity, which gives you the charge. It gives you the opposite charge, which I'll say in a moment. But in addition to that, it has something in the interior. It has non-trivial topology. And that's why its baryon number is not 0, but 1. Now, the charge has to be understood in terms of what are called self-intersection numbers. If you have two-dimensional things in 4 dimensions, then they generically will meet in some points. You count up the number of points. That's called the self-intersection number. And it doesn't change if so long as you're careful to count the signs right, the orientations. And now, if you take the electron model, that's defined in the complex projective plane with going off to infinity, and you can compactify that C2 by adding a line at infinity. You get the complex projective plane. And if you do that, the charge gets converted into the self-intersection number of a line in CP2. Well, elementary geometry, 2 lines meeting the point. That sort of goes back to Euclid. Well, in complex geometry, the same thing happens, and you get the answer +1. 2 lines meeting one point, and with orientation conventions, that corresponds to negative electric charge. So the electron has negative charge as it should do because of the geometry of this space at infinity. Now the proton, you can compactify that space to CP2 also, because we got to it by removing the real space from the complex space. So put the real space back in, you get the complex space, and now what you've got to do is to work out the self-intersection of the real projective plane inside the complex projective plane. Now that's a kind of good exercise for your graduate students in topology. It's a quite non-trivial thing to think about, because the real projective plane is non-orientable and you get all confused with signs, but nevertheless, it is well defined, it has an answer, and the answer is -1. So in the complex projective plane, there are these 2 distinguished surfaces, real surfaces. One is the complex projective line with self-intersection +1. The other is the real projective plane with self-intersection -1. And if it wasn't for that, this model would be no good. This model works, or at least passes the first test, because its topology is correct. It does give you the right charge and to compensate the charge of the electron, and it has interesting topology in the middle, which is why it's going to be a model for a baryon, not a lepton. So these properties are all important. Now let me see. Yeah. Now I'm coming to the end of my hour's talk, fortunately, because I can't say much more. All I've done so far is to indicate that in this framework, which we're trying to explore, it is possible to answer some preliminary questions, what the models should be of the basic particles. Now, of course, from there you want to go on to do lots and lots more other things to test it out. Can you break it up into pieces and so on and so forth? Can you do the dynamics? And so here are a list of some of the problems. First question is, we should have models for baryon numbers bigger than 1. The Skerr model described baryon numbers in terms of degree, and you have models for all baryon number. Here I haven't told you what manifolds are. There are a lot of manifolds in the world, and we can construct manifolds with bigger topology, and we've got to, in that lot, select the ones which we think are going to be the models we want, and they should have properties about metric. So they're quite hard to find, and we're exploring it. There are various possibilities, but I'm not yet prepared to put my money on any particular horse. I think betting in Hong Kong is very important, and I think there's building somewhere with sort of by the Jockey Club, so it has potential applications to gambling. Here I have to admit I don't know what to do yet. This is a program we've worked on for a while. We've written up the paper, and we've got lots and lots of ideas how to go further, but we're tentative, so we're not too sure this definition or that definition. We're exploring further, and I hope we'll get enough further that we can make some definite proposals. Now, if you're in compare with Riemann surface theory, there life is rather simple. Algebraic geometry tells you that every surface is algebraic. There's a genus, so you have a very easy route to follow. In 4 dimensions, or even with self-dual manifolds, there's a lot more choice. And one class of choices would come by comparing with algebraic surfaces, things of complex dimension 2. And algebraic surfaces are very well understood for 100 years, and you can classify them into sort of the surfaces which are rational, surfaces which are kind of like elliptic ones, and then the general surfaces, much like curves, can be classified in genus 0, which corresponds to the sphere, genus 1 is elliptic, genus 2 greater than or equal to 2 is general. And you can do similar things here, and from that one realizes that if you compare this problem with algebraic geometry and see what algebraic geometers have done, you find out that the very first ones are really not typical at all. The rational curves aren't indicative of curves of higher genus. So the ones with baryon number 1, which we started with, aren't really good models that indicate what's happening higher up. Something more interesting happens higher up. The next case up would be like the elliptic ones, and you might be able to get a glimmer of what to do then from some simple examples. But the general case is going to be much more complicated, and then you've got to get some general theory. I have some ideas, and one of them is to use not algebraic surfaces as examples, but more generally what are called symplectic manifolds. Symplectic manifolds are things which occur in classical mechanics, and they also occur very beautifully in the Seiberg-Witten theory, and there's lots to be known about them. They're like algebraic surfaces, but much more flexible, more choices, and I think they offer a good possibility for trying to find the right models. Second question would be, if you've done that, you want to study the moduli. How does for a given baryon number, now there won't be a unique solution. You'll have choices. If you think of it as being made up of gluing things together, is how so far apart they are when they stick together. So you expect to have some moduli, and the dynamics of the system, when you've found the right formula for the dynamics, should lead to an evolution when things can break apart. And that way you'd study what happens as you go to the boundary of moduli space, things decomposing. This would be the next problem. After you decide what the objects are, you have to decide how they decompose. Well, it's a reasonable program. We know a lot about four-dimensional manifolds. This Donaldson theory I mentioned, the Seiberg-Witten theory, are strong indications. So we could get into deep waters here and find. Third, I've added to my list of problems here. I'm not sure. I've got one. Yes, here. Then the next thing you might want to do, and if you're a mathematician or a mathematical physicist, is if you've got a four-dimensional manifold with a Riemannian metric, let's say you've got the compact case first, then you can study the spectral properties of the naturally occurring differential operators on the manifold. In this case, it would be if you had things like the Dirac operator. And they would have eigenvalues, and you can study the spectral properties of those, which will depend and reflect on the geometry of the space. So you naturally generate spectral properties, and this might then connect up with quantum mechanical ideas. So this is an obvious thing to do geometrically. If you've got a manifold, you have curvature, but the curvature shows itself in spectral properties of wave functions. So this is something, again, which we know quite a lot about. We can study it and go systematically ahead. Now that's the list of topics I had on my transparencies. Yeah, I think it's obvious. Now, but I've got a few other points which I've written down here to mention. One thing which we'd like to understand is, once you've understood how to get higher baryon number, well, first of all, you have to give a definition of baryon number. I said vaguely the baryon number, a large baryon number, should mean complicated topology in the middle. You have a region at infinity where the charge is seen, but in the core, something complicated happens. That's what you think of as roughly the position the particle is. And we'd have a number to describe that, and that would be the baryon number, and so on. But then what about the leptons? I told you what a single lepton should look like, what electron should look like. What should multiple lepton numbers as a whole be? You can make some guesses, but you like the definition of lepton number as well. It's something topological. And I don't really have an answer to that yet, but I've got some ideas. Now, related to that is the question of what's called, physicists called beta decay. If you have an electron and a proton, and you have a neutrons, well, the first approximation you might think, well, if I just glue an electron and a proton together, I might get a neutron. Or put it another way around, I might take a neutron and break it up, and I get an electron and a proton, because the proton number, the baryon number of proton and neutron are both 1, so that's preserved, and the charge of electron and the proton cancel. So when you put them together, you get charge of 0. It looks fine. Now, physicists know that's nearly true. It's not quite true, and the reason it's not quite true is the missing ingredient. When you decompose a neutron, you get a proton, an electron, and a neutrino, or an antineutrino. And the neutrino was actually invented, it's a very difficult thing to see, is invented precisely because some things weren't conserved that should be conserved. So the missing ingredient had to be there, and it was called the neutrino, and then it looked hard, and they found it. So the neutrino was the last particle to be found because it's difficult to observe, and it was necessary in order to fill the gap. The electron plus proton didn't quite match up to give you a neutron. Now, it's interesting, in this model here, something happened to the geometry. If you think of the model we've got of the electron and the proton, they both come from the complex projective plane, each by removing a certain surface, either the complex projective line or the real projective plane. So you might think, well, you just put them together, then naturally we'll get the whole space. But not quite. The reason is the two surfaces, the complex projective line and the real projective plane, you can easily check, meet in one point. You can't avoid it, it's topological. You can work out the intersection number, mod 2. You find it has to be. So these two meet in one point. And when you try to glue together the electron and the proton, you find the point is missing. You don't get the whole space. You get a space minus 1 point. So this point, in some sense, has to represent the neutrino in some way. Quite how, I don't know, but I'm thinking about it, and I hope that we'll be able to find a way of thinking about it which explains why you can decompose in this way and why the neutrino has to pop out. If you can do that, that'll be very satisfactory. It's a very simple topological picture, but the topology is quite subtle. It all has to do with the complex projective plane, but aspects of it that are really not usually studied, that are unfamiliar. But that, I think, is a hopeful thing. Now, I haven't mentioned here at all anything about the relationship with the standard theory and with quarks. Okay, quarks are meant to be the building blocks of matter, and you put elaborate theory of quarks. So, in this model, where is the quarks? What are quarks? Well, all I can suggest is that the quarks are well, they're only visible at the quantum level. And the nearest I've got to guessing is you take the complex vector plane, it can be described, a point can be described by 3 homogeneous coordinates, complex numbers, and those are, in some sense, the quarks. They are also thought of as the wave function of the solution of the Dirac equation on the background space. So they have a quantum mechanical nature. They're not points. They're complex functions. They're waves. And I suspect if there is any connection of this model with the quark model, it'll come that the quarks will be seen as corresponding to solutions of the Dirac operator on the background manifold. That's certainly consistent with what we know so far. At the same time, I haven't said anything at all about things like the generation, the fact that there are electrons come along with electrons and neutrinos, and there are other higher analogs, tau neutrinos, and so on. And these generations are, of course, important for the physics, and I don't know quite how to model those, but I'm thinking about it. There are possibilities. With a bit of goodwill, we might find them. So there's a lot more geometry to be done to make any closer link with the real physics. But I've indicated here some of the main ones. If we can get round that, then we'll have a bit more confidence that we're on the right track. We might have to modify our definitions as we go along to fit what we're looking for, and that might suggest some variations. For example, these metrics which have singularities along edges. Those are obviously quite interesting things to look about, and we might want to include those. And then, of course, once we've found the different models, we need, hopefully, we'll study the dynamics. What are the actual forces that occur? How would they interact, integrate? So you'd have some picture of disintegration of nuclei. Well, all of this is very far into the future, highly speculative. I'm surprised that the Royal Society accepted our paper for publication. There must have been some friendly referee who said, give it a chance, don't throw it out, it might not be wrong. But it's still very early days, and we're happy to have ideas from younger generation of people who can't, right? If you have any ideas, by all means join the party, work on the problem, give us some suggestions, and we'll explore it. At the moment, this is all very exploratory, but I think exploration is a very important part of research. You explore, you maybe aren't sure you're going in the right direction, you try it out and see how far you get and what conflicts. So this is what I've explained so far is the result of several years of experimentation, and we're quite happy to have got this far, but we've got a long way to go further. And if I come back to Hong Kong again, maybe next life, then I'll have some solutions for you. Thank you. Or answers. No, he's not. He's got a fundamental group of order 2, I think. And that's a point I slurred over. That because the thing you remove at infinity is non-orientable, it's not a sphere, it's a quotient of a sphere by Z2. So if you go around it, you change. So something funny is going on. Now, that may be bad for the model, it may be good for the model. I don't quite know. If you think, naively speaking, as you go to that this sphere, the sphere, if it was a sphere, would be what you would see in space outside your particle. Here's your particle. You don't know what happens inside, but go far away, you'll see some boundary. The boundary of the particle. It would normally be a sphere. Over the sphere, there's a circle, but you don't see that circle. But in the case of the model of the proton, you wouldn't see a sphere, you would see the projective plane. So as you walk around the sphere to the other side, you would change the orientation. But walking around the boundary of an elementary particle is rather difficult. How do you do it? And my hope is that the physics isn't too bad, because as you go around the particle, it is true that you come back with the opposite orientation, but at the same time, you have to reverse the orientation of the circle that lies over it. So you have to reverse time or charge. I mean, so you can't test these physics of these things geometrically. You have to do it by some physics, and the physics will really take place above, where the thing is oriented, and one lack of orientation is compensated by the other lack of orientation. So I think physically you escape from a contradiction, but geometry is still interesting, that you'd have a different behavior, little fundamental group, and whether that has a role, it's very important for the intersection number to come out right. You can't. If you double the intersection, go to the covering, you get 2 instead of 1. So it's not accidental. It's forced on you by the requirements, and it's an embarrassment in some ways, but it may be interesting in other ways. So I think at the moment it's an interesting point, which is one can study it thinking of it physically or thinking of it mathematically, and I don't quite know the right point of view. And what happens when you do more complicated baryons, it may reproduce itself. But it's a very good question.
So for the electrons,
yes.
The model is C2. Right?
Yes.
So is there any...
But the C2 is a certain metric. The non-trivial metric, not the standard metric.
Is there any spin structure you can associate with the C2?
Oh, these manifolds are spin manifolds. I mean, obviously they have complex structures. You can do the Dirac operator. Yes, they have spin structures, and I think you can argue that these are spin half. I mean, I think you can persuade yourself the model is correct from that point of view. You can certainly write down the Dirac equation and study its properties and so on. And the interesting thing is really the similarity on the one hand, the difference on the other hand between the electron model and the proton model. They some ways look very similar, and other ways look very different, and that's very important for the physics. So the geometry and the topology do reflect the key properties of the particles you're trying to make. Without that, of course, you wouldn't get started.
More question? Yeah.
We know that all our particles live in the same space.
Yeah.
By experience, but your particle, each particle stands for one space. It's one topology. Are you going to put them in one space? Interactions.
Well, you see, the idea is that these particles, the space they live in is a very small piece of our ordinary space. Here is the vacuum. When you have a particle, you put the particle in, and you little bump. The Scum model is like that. So you imagine that the field is everywhere almost constant and only has interesting behavior around one point. So the idea that they would be sort of lumps of space in some sense, almost Einstein's idea. So, and therefore, if that was the case, you would hope to combine them with gravitation in some interesting way. So it's a small variation on Einstein's idea, trying to swallow up the particles, put them in the same space. But it's an ambitious goal, and at the moment, I just think of them as models like the Scum model as a model for the nucleus, and you can study it in detail and not aim for any general theory. These are models for the nucleus, but they include charge. Therefore, they distinguish the proton and the neutron at a classical level. I mean, charge comes in ordinary theory when you quantize, and you can see the differences. But here they exist at the classical level. You see them in the topology. So that's probably related to the fact that I've taken a dual of something. So the model is richer than the Scum model. It also allows for leptons and baryons, which is, if you can do that, you've got a good deal more elaborate theory. So there are some plus features. I should say there are some, because I wrote the paper with some physics colleagues, they did some calculations and there are some numbers and scales which come out physically quite reasonable. So there's some numerical, small amount of qualitative work about numbers which are in the background, which are consistent with some physics, which I didn't mention here. So this is the mathematical side of it. When you push into the physics and do calculate some things, it finds it's consistent with the real world.
More question?
I was obviously too convincing. Or else they didn't believe a word of it. Yeah, well, don't worry. Don't take it too seriously. This is an experiment. And in fact, I'm worried that the camera there taking recording for the future. I mean, this is off the record, as they say. I don't want it to appear in the headline in the Hong Kong newspaper tomorrow, maybe you have more important things to put in the newspaper tomorrow, like the leadership of the Communist Party and things like that.
Oh, yeah. If there's no more question, that's welcome. Thanks, and Sir Atiyah.